Now that we learned a little bit about compound interest, I want to do an example that may seem a little silly, but will lead us to an observation that is pretty interesting. So what I'd like to do is I'd like to investigate what were to happen if I were to invest $1 at an interest rate of r equals 1.0. Now remember, 1.0 is the decimal form of the interest rate, so this actually represents an interest percentage of 100%. And I want to see what happens to our investment after 1 year. And again, I know this is a silly example. It's not like you would go to a bank and invest $1, but let's take a look. So we're going to take a look at what happens, that is, how much money do we have after a year, by changing n. We'll start with n equals 1, so annually, then n equals 12, that's monthly, then n equals 365, daily, and then I'm not really sure exactly how to phrase this except 10,000 times per year and 10 million times per year. So let's start out with annually. So a of 1 in this case would be 1 times, remember p times 1 plus r over n, so 1 divided by 1 to the 1 times 1 to the n times t. And now I can do this arithmetic. This is 1 plus 1, which is 2. 2 to the first power is 2. So this is just $2. So if we are compounding annually, then we'll have $2 at the end of the first year. Now at this point, if I had to guess, I would guess that we would receive quite a lot of money if we compounded 10 million times per year. Let's see what ends up happening. So for the monthly version, we do p, which is 1, times 1 plus r over n, 1 over 12, to the n times t, so 12 times t. T is 1. And we get 2.61, rounding to the nearest cent. If we go to daily, we would get 1 times 1 plus 1 over 365 to the 365 times 1. And that result would be $2.71. All right, now on to the 10,000. So for 10,000, a of 1 is going to be 1 times 1 plus 1 over, I hope you'll forgive me, I'm just going to put n here, where n is 10,000. So we're doing 1 plus 1 over 10,000 to the 10,000 power. And I will round to a higher decimal point here. I'm going to put, let's put 6 decimal points. So 2.718146. That's actually quite surprising to me. I expected on compounding 10,000 times the result to be much higher than if I were to compound only 365 times per year. Finally, we'll take a look at a of 1 when we compound 10 million, not 20 million. 1 plus 1 over, again, I'm just going to put n. Here, n is 10 million. And my calculator says that this is 2.718282. So that is incredibly close to compounding 10,000 times per year. In fact, if you round to the nearest cent, it is the exact same. And even if you round further than that, we have the same number. And if you want, you could go ahead and try out n equals 10 billion. You'll see the result is not that much different than this result. So it turns out, here's a fact, 1 plus 1 over n to the n power gets very close to a finite number as n gets very large. that finite number is about 2.718. This little squiggle equal sign means about or approximately. And this number, that 1 plus 1 over n to the n, gets very close to, comes up so often in mathematics that we have a special name for it. So the number that 1 plus 1 over n to the n power gets close to as n gets large is called e. If you have a scientific calculator or a graphing calculator, then it will have a button for e, and you can do powers of e by typing e, then the caret, and then a number. So for example, e caret 2 would be e to the second power. One example where e is useful is when you want to model your growth of money in some compound interest example where you're compounding a lot. Let me show you what I mean. Let's take a more realistic example. Let's take $10,000. So we'll let this be P. Let's take an interest rate of 2%, so 0.02. And let's have T be 20 years. And first, let's suppose that we compound 1,000,000 times. No, let's do even more. Let's do 1 billion times per year. So 1 billion is n. Then in order to figure out the amount of money after 20 years, then this would be 10,000 times 1 plus 0.02 divided by 1 billion, for which I'll just put n, times n, or not times, but 2, the n times 20 power. And if you pause here and take a look, you can see something in here that kind of looks like e. So I'll box this. This looks very similar to e. Remember, n is a billion, so n is quite large, and I'm doing 1 plus, instead of 1, I have 0.02 divided by a really large number to a really large number. And that looks almost exactly like this. That's a little hint that e will be useful in this kind of example. So let's continue with this. We have to type this into a calculator. And rounding to the nearest cent, this turns out to be 14,918 and 25 cents. Now, I alluded to e perhaps being useful in doing this type of computation. And what turns out to be true is that this computation will be approximately equal to P times e to the RT. So let's see if that works out. So, and we'll call this part B. So P is 10,000 times e to the r, which is 0.02, times t, which is 20. And it turns out that this is, rounding to the nearest cent, 14,918.25. Now, because this PE to the RT is so close to the output, or the end result of your money, when you compound a lot, we call this continuous compounding. So this is the formula for if you were to compound your money all the time, every second, every microsecond of every day. So if you invest P dollars at an interest rate R for T years compounded continuously then the amount of money A of t after t years is equal to P e to the RT. So for example, $10,000 invested at a rate of 2% for 20 years, compounded continuously, the amount of money we would have after that 20 years would be 10,000 times e to the 0.02 times 20. And of course, this ends up being our 14,918.25 that we discovered earlier. Now, one last remark about this. Typically, when we have exponential growth in practice, e is almost always used as the base of choice for the model. Of course, there are examples when that's not the case, but in general, in the sciences, e is almost always used. And so we have a definition here. The function a of t, which is lowercase a times e to the rt, if a is greater than 0 and r is any real number, this here is called continuous growth or decay. And it'll be growth or decay depending on r. If r is bigger than 0, we get growth. And if r is less than 0, we get decay. Let's take a look at a couple examples. And let's use Desmos. Now with Desmos pulled up here, let's take a look at some of these examples. So let's start with 2 times e to the x. In this case, r is equal to 1, so we're going to have, or at least we should expect to see continuous growth. Growth indicating that as the x values get larger, the y values get larger, and in fact that's the case. Also note that this graph has a y-intercept of 2, which is because if you plug in x equals 0, you get 2 times e to the 0. E to the 0 is 1, and so this is 2 times 1, which is 2. Now let's take a look at e to the 2x. In this case, r would be equal to 2. And we see we also have growth. Our y-intercept is 1. And as you go to the right, this is steeper. So this grows faster. In fact, the larger that r is, the faster you'll see growth. Let's take a look at these continuous decays. So for e to the minus x, we see the opposite behavior as we move to the right. The graph, or the y values of the graph, get smaller, eventually getting very close to 0. And for 2e to the minus 2x, we see a similar phenomenon where the decay, that is how fast the y values go down, is faster than e to the minus x. Of course, in the first example, r is negative 1, and in the second example, r is negative 2. And in general, the more negative r is, the more you can expect your graph to decay, or perhaps a bit more accurately, the faster you can expect your graph to decay. Now that we've seen some examples on Desmos of these graphs, of these continuous growth and decay examples, I think I'll just leave you with a few examples of when this is used in the real world. So continuous growth and decay, that is this exact type of model, A times e to the RT, is used in modeling populations of, could be a number of different things, perhaps some wildlife species, perhaps some bacteria in a petri dish. It's used in modeling radioactive decay, which is how we carbon date things. It's how we know how old, for example, a certain fossil is. This model is used in epidemiological models. So epi models for spread of diseases. It's used to model heat transfer. So if you want to know if you put something, let's say a very hot object, into a large cool pool, if you want to know the temperature of that object that you put in the pool after a large period of time, then this would be the appropriate model to use. And the list goes on, and you don't need to know all the details about exactly what the specifics are and how this model applies to these different real-life scenarios, but you should know that they are out there, these applications, and that's really why we study these exponential models, is to be able to model things in the real world. So I thought it appropriate to at least list some examples of why you might use this in the real world.